Okay, class, welcome to lecture 5. Today we'll be extending our discussion from single random variables to random vectors. Let's start with a basic concept, projection. For any vector x in R to the n, that is n-dimensional real space, we can define a projection function E sub I which maps from R to the n to R. This function simply gives us the ith component of the vector x. So P sub I of x equals x sub I. Now let's define the Borel sigma algebra for n-dimensional space. The Borel sigma algebra over the space R to the n, which we denote as script B of R to the n, is the smallest sigma algebra that is generated by the family of sets of the form Pi sub I inverse of B sub x. Here B sub x is an interval from minus infinity to x, inclusive, as we defined for single random variables. X is any real number and I ranges from 1 to n for each component. The elements of this Borel sigma algebra script B of R to the n are called Borel sets in R to the n. Here are a couple of reminders related to this. First, the projection function P sub I mapping from R to the n to R is itself a Borel measurable function for all I from 1 to n. Second, for any subset A of R and a projection pi sub I, the inverse image P sub I inverse of A is the set of all vectors x in R to the n such that their th component x sub I is in A. This can be visualized as R cross and so on, cross A in the ith position cross and so on, cross R. Thus, for any Borel set A in script B of R, that is the Borel sets on the real line, its inverse image under projection pi sub I inverse of A is an element of script B of R to the n. Now we can define random vectors. Consider a probability space omega script f p and a finite positive integer n. A random vector x which maps from omega to R to the n is a script f measurable mapping from the sample space to an n length real valued vector. What this means is that for any vector x in R to the n, the event A sub x of x defined as the set of outcomes omega in omega such that x sub 1 of omega is less than or equal to x sub 1 and x sub 2 of omega is less than or equal to x sub 2 and so on, and x sub n of omega is less than or equal to x sub n must be in script f. This event, a sub x of x, can also be written as the intersection from I equals 1 to n of x sub I inverse of the interval from minus infinity to x sub I, inclusive. Let's look at an example, a tuple of indicators. Consider our probability space omega script f p, a finite n and n events, a sub 1 through a sub n, all in script f. Define a vector x mapping from omega to the set 0, 1 to the n, where the ith component x sub I of omega is the indicator of a sub I evaluated at omega. Now, for any vector x in R to the n, the set A sub x of x is the intersection from I equals 1 to n of the indicator of A sub I, inverse of the interval from minus infinity to x sub I inclusive. We know from our previous lecture that the inverse image of an indicator function, that is indicator of A sub I, inverse of minus infinity to x sub I inclusive, is omega if x sub I is greater than or equal to 1, A sub I complement if x sub I is in the interval 0 to 1, including 0 but not 1, and the empty set if x sub I is less than 0. Since each of these, omega, A sub I complement, and the empty set is in script f, their intersection A sub x of x must also be in script f. Therefore, x is a script f measurable random vector. We have an important theorem that connects random vectors to random variables. Consider a probability space omega, script f, p, and a finite n. A mapping x from omega to R to the n is a random vector if and only if each of its component functions x sub I, defined as pi sub I composed with x, which just gives the ith component of x, are themselves random variables mapping from omega to R for all I from 1 to n. Let's sketch the proof. First, assume x is a random vector for any I in the set 1 to n and any real number x sub I. Consider a specific vector x in R to the n, which is infinity and so on, infinity x sub I in the eth position infinity and so on infinity. Then the set A sub x of x from the definition of a random vector simplifies. Pi sub I inverse of minus infinity to x sub I inclusive is R cross and so on, cross minus infinity to x sub I inclusive, cross and so on, cross R, which is a Borel set in R to the n. The event A sub x of x becomes simply x sub I inverse of minus infinity to x sub I inclusive, which we call A sub x sub I of x sub I. Since x is a random vector, A sub x of x is in script f. So A sub x sub I of x sub I is in script f, meaning x sub I is a random variable. Conversely, assume each component x sub I is a random variable. Then for any x in R to the n, the set A sub x sub I of x sub I, which is x sub I inverse of minus infinity to x sub I inclusive, is in script f for all I from 1 to n. The event A sub x of x is defined as the intersection from I equals 1 to n of A sub x sub I of x sub I. Since script f is a sigma algebra and is closed under finite intersections, A sub x of x must be in script f. Thus, x is a random vector. Now let's talk about the distribution of random vectors. Consider our probability space omega script f, p, and a finite n. The joint distribution function of a random vector x mapping omega to R to the n is defined as a mapping f sub x from R to the n to the interval 0 to 1. For any vector x in R to the n, f sub x of x is defined as the probability of A sub x of x, which is probability of the intersection from I equals 1 to n of A sub x sub I of x sub I. Let's revisit our example of a tuple of indicators. Consider omega script f, p, a finite n, and events a sub 1 through a sub n in script f, defining the random vector x as indicator a sub 1 and so on, indicator a sub n. For any x in R to the n, let's define two index sets. I sub naught of x as the set of indices I in 1 to n for which x sub I is less than 0, and I sub 1 of x as the set of indices I in 1 to n for which x sub I is in the interval 0 to 1, including 0 but not 1. Then the joint CDF f sub x of x can be expressed as follows. It's 1 if both I sub naught of x and I sub 1 of x are empty, meaning all x sub I are greater than or equal to 1. Its probability of the intersection for E in I sub 1 of x of a sub I complement if I sub naught of x is empty, but I sub 1 of x is not empty, meaning all x sub I are greater than or equal to 0. And for those in the interval 0 to 1, including 0 but not 1, we need the indicator to be 0. And it's 0 if I sub naught of x is not empty, meaning at least one x sub I is less than 0. So one of the conditions x sub I is less than or equal to x sub cannot be met by an indicator variable. This leads to the concept of marginal distribution for a random vector x mapping from omega to r to the n defined on omega, script f, p, and for any component I in 1 to n, the distribution of x sub I, which is pi sub I composed with x, a random variable from omega to r, is called the ith marginal distribution. We denote it by f sub x sub I mapping from omega. This should be r to the closed interval 0 to 1. Let's apply this to our tuple of indicators example. X is indicator a sub 1 and so on, indicator a sub n. The ith marginal distribution f sub x sub I of x, where x is a scalar here for the component, is 1 minus probability of a sub I times the indicator of the interval 0 to 1, including 0 but not 1, applied to x, plus the indicator of the interval 1 to infinity, including 1, applied to x. This is just the CDF of a Bernoulli random variable. We have a corollary regarding marginal distributions. Consider a random vector x from omega to r to the n, defined on omega, script f, p with a joint distribution function f sub x from r to the n to the closed interval 0 to 1. The ith marginal distribution f sub x sub I of x sub I can be obtained from the joint distribution f sub x by taking the limit as all other components x sub j for j not equal to I go to infinity. So f sub x sub I of x sub I equals the limit of f sub x of x as x sub j approaches infinity for all j not equal to I. The proof follows from one of the equations we saw earlier, which stated that x sub I inverse of minus infinity to x sub I inclusive equals a sub x of x, where x is infinity and so on, x sub I and so on, infinity. Taking probabilities gives the result. Now let's list the properties of the joint distribution function. Consider x mapping omega to r to the n defined on omega script f p. Its joint CDF f sub x satisfies 1 for any two vectors x, y in r to the n such that each component x sub I is less than or equal to y sub I. For all I in 1 to n, we have f sub x of x is less than or equal to f sub x of y. This is multivariate monotonicity. 2. The function f sub x of x is right continuous at all points x in R to the n. This means if we approach x from a direction where all components are decreasing towards x sub I, the limit is f sub x of x. 3. The lower limit as any x sub I approaches minus infinity of f sub x of x is 0. And the upper limit as all x sub I approach infinity for all I in 1 to n of f sub x of x is 1. Let's briefly touch on the proof of these properties. Let x be our random vector. 1. If x sub I is less than or equal to y sub I for all I, then the event a sub x of x, which is all x sub j less than or equal to x sub j, is a subset of the event a sub x of y, which is all x sub j less than or equal to y sub j. So by monotonicity of probability, f sub x of x is less than or equal to f sub x of y. 2. The proof for right continuity is similar to the proof for a single random variable involving limits of sequences of sets. 3. For the limits, the event a sub x of x becomes the empty set if any x sub I goes to minus infinity. So its probability is 0. The event a sub x of x becomes the entire sample space omega if all x sub I go to infinity, so its probability is 1. The result follows from the continuity of probability. Let's look at an example concerning the probability of rectangular events for a 2D random vector. Consider omega script f, p, and a random vector x from omega to r squared. Consider points x and y in r squared with x sub 1 less than or equal to y sub 1 and x sub 2 less than or equal to y sub 2. Let b sub 1 be the event x sub 1 less than x sub 1 is less than or equal to y sub 1, which is a sub x sub 1 of y sub 1 minus a sub x sub 1 of x sub 1. Let b sub 2 be the event x sub 2 is less than x sub 2 is less than or equal to y sub 2, which is a sub x sub 2 of y sub 2 minus a sub x sub 2 of x sub 2. Both b sub 1 and b sub 2 are in script f. The marginal probabilities are probability of b sub 1 equals f sub x sub 1 of y sub 1 minus f sub x sub 1 of x sub 1, and probability of b sub 2 equals f sub x sub 2 of y sub 2 minus f sub x sub 2 of x sub 2. Continuing this example of probability of rectangular events, let x equal x sub 1, x sub 2, and y equal y sub 1, y sub 2. The rectangular event b sub 1 intersect b sub 2, which is x sub 1 is less than x sub 1 is less than or equal to y sub 1, and x sub 2 is less than x sub 2 is less than or equal to y sub 2 has its corners defined by. Now let's discuss the event space generated by random vectors. Consider omega script f p and a finite n. The event space generated by a random vector x from omega to r to the n is the smallest sigma algebra that is generated by the collection of events a sub x of x for all x in r to the n. We denote this as sigma of x, which is sigma of the set a sub x of x for x in r to the n. We have a theorem relating the sigma algebra of a random vector to those of its components. Consider a probability space omega script f p, a finite n, a random vector x from omega to r to the n, and its component projections x sub I equals pi sub I composed with x. Then the sigma algebra generated by the random vector x, sigma of x, is equal to the sigma algebra generated by its components x sub 1 through x sub n, denoted sigma of x sub 1 and so on, x sub n. Let's look at the proof. Sigma of x is generated by the family of events a sub x of x for x in r to the n, sigma of x sub 1 and so on. X sub n is generated by the family of events a sub x sub I of x sub I for x sub I in r and I in 1 to n. We know a sub x sub I of x sub I is equal to a sub x of x, where x is infinity and so on, x sub I and so on, infinity. This means any generator for sigma of x sub 1 and so on, x sub n is in sigma of x, hence sigma of x sub 1 and so on, x sub n is a subset of sigma of x. Conversely, a sub x of x is the intersection from I equals 1 to n of a sub x sub I of x sub I. This means any generator for sigma of x can be formed from elements that generate sigma of x sub 1 and so on, x sub n. So sigma of x is a subset of sigma of x sub 1 and so on, x sub n. Since they are subsets of each other, they must be equal. For our tuple of indicators example, consider omega script f p, a finite n, and events a sub 1 through a sub n in script f, defining x equals indicator a sub 1 and so on, indicator a sub n. The sigma algebra generated by x, sigma of x, is equal to the sigma algebra generated by the events a sub I for I in 1 to n, that is sigma of a sub 1 and so on, a sub n.
Next, we revisit the independence of random variables, now in the context of random vectors. Recall the definition: a family of collections of events, script a sub I, a subset of script f for I in I, is independent if for any finite f a subset of I and any a sub I in script a sub I for I in f, probability of the intersection of a sub I equals the product of probability of a sub I.
Now for independent and identically distributed random variables within a vector, a random vector x from omega to r to the n defined on omega script f p is called independent if its joint CDF f sub x of x factors into the product of its marginal CDFs. That is f sub x of x equals the product from I equals 1 to n of f sub x sub I of x sub I for all x in R to the n. The random vector x is called identically distributed if each of its components x sub I has the identical marginal distribution, that is f sub x sub I equals f sub x sub 1 for all I in 1 to n. Some reminders regarding independence of random vectors. If a random vector's components are independent, then the events a sub x sub I of x sub I for I in 1 to n are independent for any choice of x sub 1 through x sub n. If we define family's script a sub I as the collection, a sub x sub I of x for x in R for each I, then the statement of independence of components means these families script a sub 1 and so on, script a sub n are mutually independent. In general, if two collections of events are mutually independent, then the event spaces or sigma algebras generated by them are also independent. This is a deeper result that can be proved using Dynkin's pi lambda theorem. This leads to a theorem for an independent random vector x, meaning its components are independent as per the CDF factorization defined on omega script fp. The event spaces generated by its components sigma of x sub I for I in 1 to n are independent. The proof outline is define the family of events script a sub I as x sub I inverse of minus infinity to x inclusive for x in R for each I. The independence of the random vector x means these families script a sub I for I in 1 to n are mutually independent. Since sigma of script a sub I is just sigma of x sub I, the result follows from the previous remark that independence of generating classes often extends to independence of the generated sigma algebras under certain conditions like those met by P systems. We can also define independent random vectors, two random vectors x from omega to R to the n and y from omega to R to the m defined on the same probability space. Omega script f p are said to be independent if the collection of events a sub x of x for x in R to the n and the collection of events a sub y of y for y in R to the m are independent. Here a sub x of x is the joint event for x and a sub y of y is the joint event for y. Essentially, any event defined by x is independent of any event defined by y. Let's see an example of independent random vectors. Consider a state space script x equals the set containing the vectors 0, 0, 1 and 1, 0, 0, which is a subset of R cubed. Consider two independent coin tosses. So omega equals the set h t squared. Script f is the power set of omega and probability of omega equals p to the k sub 2 of omega times 1 minus p to the power of 2 minus k sub 2 of omega, where k sub 2 of omega is the number of heads in the two tosses for outcome omega. Let x be the vector 0, 0, 1 times indicator that omega sub 1 equals h plus the vector 1, 0, 0 times indicator that omega sub 1 equals t. Let y be the vector 0, 0, 1 times indicator that omega sub 2 equals h plus the vector 1 0 0 times indicator that omega sub 2 equals t. Here x and y mapping from omega to r qubit are mutually independent random vectors because x depends only on the first toss and y only on the second, and the tosses are independent. However, note that within x, the components x sub 1 and x sub 3 are dependent random variables. If x sub 1 equals 0, x sub 3 equals 1, and if x sub 1 equals 1, x sub 3 equals 0. The same applies to y sub 1 and y sub 3. Now let's talk about discrete random vectors. If a random vector x mapping from omega to script x, sub 1 cross and so on, cross script x sub n, which is a subset of r to the n, takes on only a countable number of values in r to the n, then it is called a discrete random vector. That is, the range of the random vector x is countable. Such a random vector is completely specified by its joint probability mass function, or PMF, p sub x of x, which is probability of the intersection from I equals 1 to n of x sub I equals x sub I for all x in the product space script x sub 1 cross and so on, cross script x sub n. As a reminder, for an independent discrete random vector x from omega to r to the n, meaning its components are independent, its joint PMF factors p sub x of x equals the product from I equals 1 to n of p sub x sub I of x sub I for each x in r to the n. Let's look at an example of multiple coin tosses as a discrete random vector. Consider a probability space where omega equals the set h t to the n, script f is 2 to the omega, that is the power set, and probability of omega is 1 over 2 to the n for all omega in omega, which is the fair coin assumption. Consider the random vector x mapping from omega to r. This should be r to the n, such that x sub I of omega is the indicator that omega sub I equals h for each I in 1 to n. This x is a bijection from the sample space omega to the set 0, 1 to the n. In particular, x is a discrete random vector. For any x in the set 0, 1 to the n, let n of x be the sum from I equals 1 to n of the indicator that x sub I is in the interval 0 to 1, including 0 but not 1. This denotes the number of zeros in the binary random vector x of length n. The joint distribution f sub x of x is 1 if all x sub I are greater than or equal to 1. It is 1 over 2 to the power n of x. If for all I, x sub I are in the interval 0 to 1, including 0 and 1, and 0 if any x sub I is less than 0. Continuing the example of discrete random vectors for multiple coin tosses. We can derive the marginal distribution for the ith component x sub I. F sub x sub I of x sub I is 1 if x sub I is greater than or equal to 1, 1/2 if x sub I is in the interval 0 to 1, including 0 but not 1, and 0 if x sub I is less than 0. This is the CDF of a Bernoulli 1/2 random variable. Therefore, it follows that X is an IID random vector that is independent and identically distributed components. Finally, let's touch on continuous random vectors. For a jointly continuous random vector X from omega to r to the n with a joint distribution function f sub x, there exists a joint density function f sub x from r to the n to non-negative reals such that f sub x of x is the nth order mixed partial derivative of f sub x of x with respect to x sub 1 through x sub n, and f sub x of x is the integral of f sub x of u sub 1 and so on, u sub n, where u sub 1 is less than or equal to x sub 1 and so on, u sub n is less than or equal to x sub n. As a reminder, for an independent continuous random vector x, where components are independent, its joint density function f sub x of x factors into the product of its marginal density functions, f sub x of x equals the product from I equals 1 to n of f sub x sub I of x sub I for all x in r to the n. Let's consider the example of Gaussian random vectors. For a probability space omega script f p, a Gaussian random vector is a continuous random vector x from omega to r to the n defined by its joint density function f sub x of x equals 1 over the square root of 2 pi to the n times determinant of sigma times e to the power of minus 1/2 times x minus mu transpose times sigma inverse times x minus mu for all x in r to the n. Here mu in r to the n is the mean vector and sigma in r to the n cross n is the positive definite covariance matrix. The components of such a Gaussian random vector are themselves Gaussian random variables. They are independent if and only if the covariance matrix sigma is a diagonal matrix. They are identically distributed if sigma is a scalar multiple of the identity matrix. Sigma equals sigma squared I, and all components of mu are equal. This concludes our overview of random vectors, their distributions, and the concept of independence for random vectors.